In this presentation, I am going to explain steady state stability of electric drive. Coming to the steady state stability, the basic relation of the dynamic torque equation of motor load system, that is electromagnetic torque produced by the motor equal to load torque plus J into d omega m by dt. This is dynamic torque. This is present only during the transient operation, like either starting or braking or speed accelerating or decelerating, like that. During that period only this component, that is dynamic torque, will be present. Therefore, this is the equation T equal to TL plus J d omega m by dt. Under steady state condition, d omega m by dt equal to 0 or T equal to TL. That is, the torque produced by the electromagnetic torque produced by the motor, that is equivalent to the load torque. That is what we call it as steady state condition. Now coming to this plot of this one. Now this is assume that this is the speed torque characteristics of a induction motor. Assume that's an induction motor. And this is the omega m axis and this is taken as the torque axis. Therefore the speed torque axis of capital T or the motor. And the load is having a fan load or whatever, some compressor, etc. This is the load characteristics TL. Therefore TL versus omega m is this one, T versus omega m is this one, and the point of intersection, that is a point, is A. Now this is the at this point of A, T equal to TL, or meaning that if the motor is working at this condition that we call a steady state point or stability, there the d omega m by dt will become 0 and the motor torque is equal to the load torque. Therefore, drive will operate in the steady state when the motor torque is equal to the load torque. At the point A, motor torque equal to the load torque. In motor drive system, electrical time constant of the motor is negligible compared to the mechanical time constant. Now, the figure shows the speed torque characteristics of a motor and a load, and capital T is the motor torque and TL is the load torque. This is the motor torque and this is the load torque axis and omega m axis, and this is the steady state. This is a stable operating point, a steady state point where d omega m by dt equal to 0. Continuing the steady state stability, here as already we have seen, this is the motor torque characteristics and this is the load torque characteristics. This is the operating point. Point A is the operating point. So speed torque characteristics of a motor and load intersect at the point A, and that we call it as operating point. Now to check whether this operating point A is stable or not, provide a disturbance or a perturbance, we call it perturbance or disturbance, either in plus omega m or minus, or plus delta omega m or minus delta omega is provided. But from this one, some disturbance we are providing, either will be providing a plus delta omega m and minus delta omega m, and if that point is returning to back to this A, then we call it that the point A is stable. Now operating point will be momentarily shift to C or point B by this variation delta omega. Either it will be moving to a C, or if it is a plus on delta omega m, or it is moving to B momentarily when it is a minus delta omega m. And if it is coming back to the point A, we call it as that point is stable. And the corresponding to the point C, if you see that one, if it is momentarily it is shifted to the point C here, corresponding to this point C here, if you see that one, the motor torque is, that is, this is a motor torque and this is the load torque. Motor torque is less than the load torque. We can say that one. Or load torque is more than motor torque. TL is more than T. Or since TL is more than T, as per this equation, T minus TL equal to J d omega by m by dt. Since TL is more than this one, J d omega m by dt will become negative, or d omega m by dt will become negative, meaning that speed is getting down. That is, speed is getting down means the point will be coming back towards A. Therefore, as per this equation, d omega m by dt will be negative since TL is more than T, negative, and the speed reduces and hence the operating point moves towards A. That is, even though it is shifted to temporarily, it will be coming back to the point that will be shifted to the point A. Similarly, if you are providing a minus delta omega and disturbance, the point momentarily it is shifting to the point B. At point B, similarly, if the operating point is shifted to the point B, due to the disturbance, T is greater than TL. At the point P, we can see that the motor torque is more than the load torque. T is more than TL. In that case, since T is more than TL, J d omega m by dt positive or d omega m by dt is positive, meaning that it will be accelerating. Since T is more than TL, hence d omega m by dt will be positive and the speed increases and operating point will be moving towards the point A. Now, if it is, even though momentarily shifted to B, since the motor torque is more than the load torque here, there will be d omega m by dt will be positive and it is getting speed is going increasing and that will be moving the point from the B to A. This indicates that the operating point is a stable equilibrium point. This is called a stable equilibrium point, in that even though you are giving a disturbance to C, that is coming back to A. Similarly, if it is disturbance to B, that is coming back to A. That is why this operating point is called stable equilibrium point. Continuing the steady state stability. And here there are 4 graphs are shown here. This is A, B, C and D. This is the point A and this is point B and this is point C. Now coming to this one, the point A is stable in the case. The same argument as I already explained. If you give a perturbance, as an example, if it is shifted towards here, that is a perturbance, or if there is a reduction in speed here, is you can see that motor torque will be more than the load torque. Once motor torque is more than the load torque, T minus TL will become positive and d omega m by dt will become positive, or speed is increasing. Therefore, it is coming back to this point. Same way, if this operating point is shifted towards here, you can see that TL is more than T, or T minus TL will be negative, or d omega m by dt is negative. That is why the operating point, it is decelerating, that is coming to this one. For this is a stable equilibrium point. The point A is a stable equilibrium point. Same argument can be given the second quadrant operation here also. In second quadrant operation, that is a C here, this is also stable in the sense, if you are giving a perturbance, for example, from the C point we are giving a perturbance to this point. Now what happens here? This point, the motor torque is more negative compared to, this is a negative second quadrant. Therefore, motor torque is more negative compared to the load torque. Therefore, T minus TL becomes, that is the negative. T minus TL becomes negative since this is a more negative. That is why T minus TL is negative, means that d omega m by dt equal to negative, or that will be speed is getting down, that will be coming to the point C. Same thing here also, the reverse case, in that case speed will be increasing and that will be coming to this point C. That is why the point C is also a stable equilibrium point. Therefore, the point A and C are the stable equilibrium points. But if you come to this characteristics like this one, this is the motor torque and this is the load torque. Same argument if you see that one. If a perturbation, due to a perturbation, either the speed is increasing or decreasing. If it is increasing here, you can see that this point is not stable. Therefore, if you take this one, if you take a operating point somewhere here, you can see that motor torque is more than the load torque. Since the motor torque is more than load torque, T minus TL become positive, or d omega dm dt positive. That is why the speed is getting increased. That is why if at all any perturbation is there towards this side, it won't come back to this one. It will be going away from that one. That is why this point is not stable. This is a unstable equilibrium point. Similar argument can be extended to this one also, which is operating in the second quadrant. This is also unstable. Therefore, A and C are the stable equilibrium points. B and D are the unstable equilibrium points. Point A and C are the stable equilibrium points. Points B and D are the unstable equilibrium points. For a point to be stable equilibrium, the condition to be satisfied, we will be deriving the next slide with the condition. The condition is that the slope of the load line with respect to omega m should be more than the slope of the motor line with respect to omega m, or dTL by d omega m should be more than dt by d omega m. The previous slide we have seen that the condition to get for stable equilibrium point is dTL by d omega m should be more than dt divided by dt by d omega m. Now let us see how this can be derived. For that one we are considering a motor torque characteristics as well as a load torque characteristics, and this is a point of intersection where it is stable equilibrium point. Now here consider a speed torque characteristics of the motor and the load torque as shown in the figure. Point of intersection is the operating point. This is the operating point. It means that the motor runs with a corresponding torque and speed. That is, this is the at this speed with this torque that is motor is running. Now let us see a perturbation or a disturbance is given. Now a small disturbance or perturbation in speed results. Therefore, a small disturbance of delta omega m is provided. A small disturbance of delta omega m is provided. The disturbance towards motor torque is equal to delta T, and disturbance towards load torque equal to delta TL. Therefore, if the basic equation for the load torque and motor torque equal to T equal to TL plus J d omega m by dt, that we are representing as the equation 1. Now due to this perturbation or disturbance, T is increasing T plus delta T, and TL is increasing by TL plus delta TL. Therefore T plus delta T equal to TL plus delta TL plus J d omega m plus delta omega m, or T plus delta T equal to TL plus delta T plus, this is we are expanding, J into d omega m by dt plus J into d delta omega m by dt. This is the second equation. Continuing the derivation of condition for the stable equilibrium point, that is this one. As we have already seen, T equal to TL plus J d omega m by dt, giving a perturbation for delta omega m, T plus delta TL equal to TL plus delta TL plus J d by dt of omega m plus delta omega m, or T plus delta TL equal to T plus delta T equal to TL plus delta TL plus J into d omega m by dt plus J d delta omega m by dt. It's equation 2, as we have already seen. Now if you subtract the second equation from first equation from the second one, subtract this equation from the second equation, then we'll be getting delta T equal to delta TL plus J d delta omega m by dt, or G d delta omega m by dt equal to delta T minus delta TL, or this is equal to delta T minus delta TL. That is represented as equation 3. Now for a small perturbation, the speed torque curves can be approximated as straight line. That is, for if the disturbance is very less, it can be approximated as a straight line. Under this condition, delta T by delta omega m can be equated to dt by d omega m, or delta T can be written as dt by d omega m into delta omega m, and delta T by delta TL by delta omega m equal to dTL divided by d omega m, or delta TL equal to dTL divided by d omega m into delta omega m. Therefore, this is the equation for delta T, and this is the equation for delta TL. Substitute this delta T and delta TL in equation 3, then we will be getting what is J d delta omega m by dt. Continuing the derivation for the condition for the stable equilibrium point, already we have seen the equations for delta T and delta TL. In the last slide we have seen the equation, and we are substituting this delta T and delta TL in this equation 3, and substituting 4 and 5 in equation 3, then we will be getting J into delta d delta omega m by dt equal to dt by d omega m into delta omega m minus dTL divided by d omega m into delta omega m, or here J into d delta omega m by dt equal to dt by d omega m minus dTL by d omega m into delta omega m, or we are as an equation, if you write it as say first order differential equation, in a differential equation, here J into d delta omega m by dt plus this one dTL divided by d omega n minus dt by d omega m into delta omega m equal to 0. Therefore, this is a first order differential equation in which you can take the variable as a delta omega m. But just like delta omega m, if you take x as like j dx by dt plus some constant into x equal to 0. Therefore, x is the unknown. Like that one, delta omega m can be taken as the variable that is an unknown variable. The solution is that delta omega m, we have to find out the solution for this delta omega m, and that delta omega m is equal to delta omega m naught, that is initial value of delta omega m, into e to the power of minus 1 by j into this one dTL by d omega m minus dt by d omega m into t. Therefore, this is a solution of this first order differential equation for the delta omega m, that is the variable, that is the change in speed, delta omega m. This is the equation for delta omega m. Continuing the derivation for the condition, derivation of the condition for the stable equilibrium point. This is the motor torque, as I already said. This is the motor torque and this is the load torque. This is the equilibrium point. We are giving a perturbation in speed, delta omega m, and delta TL and delta T are the corresponding change in load torque and motor torque. Now the solution, as we have seen in the last slide, delta omega m equal to delta omega m naught into e raised to minus 1 by j dTL by d omega m minus dt by d omega m into time t. An operating point will be stable when delta omega m approaches to 0 as time t tends to infinity. As time t tends to infinity, if delta omega m approaches to 0, then we call it as this operating point is stable. Meaning that for this to happen, to become stable here, this is to happen, this term, that is minus 1 by j into dTL by d omega m minus 1 by dt by d omega m, that should be less than 0. This is the condition. Then only that will become stable. If only this condition should be less than 0, then only that will be settled into in a stable case. Stable, that is operating point will be stable. Or we can say that one minus, if you take j is removing, minus of dTL by d omega m minus dt by d omega m should be less than 0. It should be negative. Or dTL by d omega m minus dt by d omega m should be more than 0. Or dTL by d omega m should be more than dt by d omega m. Therefore, the condition for this operating point or to be stable as a stable equilibrium point is that the slope of this load curve with respect to omega m should be more than the slope of the motor curve with respect to omega m. That is, dTL by d omega m should be more than dt by d omega m. This is the condition for this equilibrium point to become a stable equilibrium point. Coming to a problem, a motor when operating in quadrant 1 and 2 has the characteristics T equal to 400 minus 0.4 n. N is the speed, that much Newton meter, where n is the speed in RPM. The load which is coupled to the motor is active load with a characteristics load torque equal to plus or minus 200 Newton meter. Calculate the motor speed for motoring and braking operation in the forward direction, that is first quadrant as well as second quadrant. When the drive is operating in quadrant, the second part of the question is that when the drive is operating in third and fourth quadrant, motor has a characteristics equal to T equal to minus 400 minus 0.4 n Newton meter. What will be the equilibrium point in the quadrant 3? Therefore, these are the questions in which first let us see that speed corresponding to load torque equal to plus 200. That is the first quadrant operation. Load torque equal to plus 200 and the motor torque is given by 400 minus 0.4 n Newton meter. That's the first quadrant operation. To find the operating point, we have to equate the motor torque with the load torque. That is the equilibrium point at which that motor will be running. Therefore, the motor torque is equated to the load torque. That is 400 minus 0.4 n. That should be equated to 200. Or n is equal to 500 rpm. For the speed of the motor in the forward direction, that is that will be running at the speed with this much load, that is equal to 500 rpm. That's the first quadrant operation, forward motoring. Now coming to the second case, that is called forward braking operation, the second quadrant operation. To find the speed corresponding to the braking, corresponding load torque is given as minus 200 Newton meter. Therefore again we can have equate the motor torque to the load torque. That is, in the second quadrant of operation, T equal to TL, that is equilibrium point. To find out when T equal to TL, or 400 minus 0.4 N equal to minus 200, or N equal to, we can say N equal to, it is equal to 1500 rpm. That is corresponding to the second quadrant of operation. Motor speed for braking operation in the forward direction, that second quadrant, that we call it, it is equal to 1500 rpm. Therefore in both cases we have to equate the motor torque to the load torque. Then will be that the corresponding speed n is that equilibrium point at that the load condition. Second part of the question here, that is operating in either in third and fourth quadrant. The drive is operating in third and fourth quadrant. Then motor torque is, now it is changing, T equal to minus 400 minus 0.4 N is rpm, that much Newton meter, and the load torque is given as minus 200, that much Newton meter. Again, to find out the equilibrium point, you have to equate the T and TL. To find the speed corresponding to the equilibrium point, the motor torque is equated to the load torque, or minus 400 minus 0.4 N, that is equal to minus 200. Now what is the corresponding N? N is equal to, we'll be getting, it is equal to minus 500 rpm. Therefore this is the speed corresponding to the third quadrant for this load torque, TL equal to minus 200 Newton meter, and this is the motor torque. Another problem, a drive has the following parameters: T equal to 150 minus 0.n, that's rpm, that much Newton meter, where n is the speed in rpm, and load torque is given as 100 Newton meter. Initial drive is operating in steady state, and characteristics of the load torque is now changing to TL equal to minus 100 Newton meter. Calculate the initial and final equilibrium speeds. Again, the principle, as I already explained in the previous slides, you have to equate the motor torque to the load torque, and you have to find out the corresponding speed. Now initially the motor torque is equal to 150 minus 0.1 N, that is given, and load torque is given as 100 Newton meter. Now if you are equating this T equal to TL, that is at equilibrium speed, motor torque is equal to the load torque. Therefore 150 minus 0.1 N, that should be equal to 100, or speed N is equal to, you can calculate, it is equal to 500 rpm. That is the initial equilibrium point. Now after this one, the characteristics of the load torque is now changed to minus 100 Newton meter. That is, finally T is equal to same as that one, 100 minus 0.1 N, but TL has now reversed. TL equal to minus 100 Newton meter. Therefore at equilibrium speed, you have to equate these two, that is motor torque and equal to the load torque, or 150 minus 0.1 N, that is equal to minus 100, or N equal to, if you calculate, we'll be getting, it is equal to 2500 rpm. That is the final equilibrium point corresponding to a load torque of minus 100 Newton meter and a motor torque of this much, 100 minus 0.1 N.